So, the spectra of stars. We've previously talked about black body radiation and the ultraviolet catastrophe, and we've also talked about emission and absorption spectra, two different ways of producing light. I'm going to try to distinguish between them and explain how they work together to make sunlight. So, when you have a big star like the sun and it's shining, there are two things going on here. One is black body radiation. That's where the charged particles of the sun, the protons and the electrons, they're so warm that they're vibrating, and that vibration releases light. And that light is released in the normal sort of black body curve, which if we look at frequency versus intensity of light, if this is low frequency, we get some kind of curve looking like this for our sun peaking around the green light, making the sun look overall whitish or whitish yellow. Yep, peaking around there. Now, that is different to the electrons in the hydrogen atoms jumping up and down. So there's hydrogen gas in the sun. The hydrogen atoms have electrons, and those electrons, when they jump up and down shells, when they jump up, they need to absorb photons of the exact energy. That's the difference between the levels they're jumping from. And when they jump back down, they will release that same energy of light. So we usually display this as if we look at a continuous spectrum. So we have frequency again from red on the left to blue on the right. If we energize some hydrogen and it releases light, it's going to release one red bit of light, which corresponds to the third shell, an electron in the third shell jumping down to the second. It will release this red photon of light. If it's in the fourth, jumping down to the second, it's going to release this green photon of light. If it's in the fifth or the sixth, it's going to release a couple of blue-ish photons of light. Okay, and this is all in the visible spectrum. It does do stuff in the infrared and in the ultraviolet as well, but let's just look at this for now. So, yeah, one of these is just because it's a hot black body. The other one is because you've got a hydrogen atom with electrons that are jumping down from one shell to another, releasing photons like this photon here. Okay, two different things. So when we look at the light coming from the sun, what do we see? How do these two things combine? Well, we see the curve of the black body radiation. So let's draw it in here. I'm going to cut out half of that. Black body. So we see this curve, but at the spots where the hydrogen is going to be absorbing these particular colors of light, at those spots, the black body is going to dip. So, in fact, I'm going to redraw this. So, yes, it's going to curve up. However, where that red line appears, zoink, it's absorbed a bit of that light. And then the curve keeps going, but at that green spot, zhunk, it's absorbed a bit of that light. And then at those blue spots, zhunk and zhunk, it's absorbed those lights, and then it's coming down. Okay, so the normal, I've drawn this a bit high. So the normal black body radiation curve, except with some chunks taken out because the hydrogen has been absorbing those chunks. Okay, this is the combination of the emission and absorption spectra plus the black body spectrum added together coming out from the sun. And this is the two different causes of the thing. Black body because hot ions are vibrating, absorption emission spectra because electrons are jumping up and down shells. Now, let's look at the stellar spectra and describe how they're used to classify stars. So this overall spectral graph will get a peak frequency or a peak wavelength of light from that. And depending on what that peak is, that tells us about the temperature and the color of the star. They're actually directly related. We can go over to our formula sheet, quantum special relativity nuclear. We get this equation here. The maximum wavelength, that's the wavelength with the max intensity, is proportional to the temperature of that star. So in this case, this wavelength here, whatever that happens to be, that's going to be proportional to the temperature of our star. ours, for example, the peak one is going to be around this green wavelength. That's going to say that our star has a very average temperature, maybe even a little cooler than other stars. Okay, now sometimes this peak can be somewhere we don't expect it to be, but we can work out exactly where it should be because we know where these lines should be positioned. So if all of those lines are positioned slightly to the left or the right, we know that it's just a blue shift or red shift of the star because it's moving towards or away from us. We can adjust for that and work out exactly what this peak frequency should be. Let's now talk about the Hertzsprung-Russell diagram. So it's going to use this information that I just mentioned. Here we go, get rid of all those bits. So the Hertzsprung-Russell diagram is a graph, and on one side we have the color or the temperature of the star. Okay, and we know that those two things are in proportion to each other, so we can label that axis as either of those things. So our sun, like I said, it's going to have a reddish color. So down here, or like a whitish yellowish color here. We're going to have red down this end here. You don't get green stars because the green part of the spectrum is going to blend the blues and the reds equally with the greens, making a whitish star. So it goes from red, whitish in the middle, and then blue up at this end here. Okay, so our star is kind of a coolish star, so towards the red. And on the other axis, you have the luminosity, which is the amount of light energy that comes out of a star. Irrelevant of how far away it is, we pretend they're all the same. If we talk about brightness, they can be more bright if they're closer, less bright if they're further away, but luminosity is unaffected by that. So when we count the luminosity as well, our sun's pretty average, maybe a little bit below average. So our sun will end up around here, below average luminosity, below average temperature, however, nothing too crazy, right in the middle. And it's part of what's called the main sequence of stars. So there's a group of stars that sort of follow this line here. There's a whole bunch of them, two slightly big blue ones up here, two normal ones like our sun, and then some smaller reddish ones down this end here. And this is telling us about the evolutionary stage of the star. If they're in this line here, they're new stars. That's their evolutionary stage. They've just been born from clouds of gas. Their characteristics, they will be fusing in their cores and not doing much else than that. However, when their core runs out of fuel, the star will cool down, which will allow gravity to take hold. Because normally a star, say our sun, is a balance of the heat from the inside pushing it out, but the gravity of the star pushing it in. And these two things are balanced, keeping the star at a stable shape. But when the core stops being able to fuse, because it's fused all its hydrogen into helium, this outward pressure stops, the inward pressure takes over, and it kind of bounces, right? Well, it doesn't bounce at this point. It squeezes in, triggering a second lot of fusion around the core, and that second lot of fusion has enough heat to expand the star. So surprisingly, reducing the fusion shrinks it, which triggers new fusion, which expands it, and the overall effect is the star getting bigger. So our sun will actually jump up, increasing in luminosity because it's getting bigger in size, but decreasing in temperature also because it's increasing in size. So it's going to become a red giant over here. Okay, so if we see that a star is sort of in this section here, its evolutionary stage is that of a red giant. And when it's doing that, it's fusing not in its core, but around the core in a secondary layer. That's what a bigger star like this blue one I've drawn up here, when it gets to that stage, it's going to jump over here and become a supergiant, something in this area here. It could still be quite bluish if it's on this end, be really, really big, or it can be a red supergiant, really big one over here. Oops, shouldn't draw red there. Now, when a giant like our sun might become one day, when it runs out of fuel again, the internal pressure decreases, and gravity takes over. And this time there's no new fusion to take place. Gravity's just taking over. It's going to very, very rapidly crunch all of that gas in. However, its gas is quite elastic. It crunches in and then poofs outwards, and we get a nova. That gas is going to fly away and become a nebula, a cloud of gas. For these big guys up here, they're a bit more dramatic. When they crunch in, they can sometimes crunch in so hard that they fuse the nucleuses of lots of atoms together to form a neutron star, or they can crunch in so hard that they fuse all matter into a single point and result in a black hole. So these two can do that, which is amazing. But these guys here, they're going to, after they've done their nova, they're going to drop down here, whatever's left of them, and become a little white dwarf, in fact. I should make it more of a whitish color. Let's go like this. They become a white dwarf, which is the small core left over. It's very, very hot, but it's no longer fusing, and it's just going to drift down here towards the red end of the spectrum as it cools down over time, eventually hitting the very bottom here where it's a brown dwarf, where it has no color and no luminosity because it's not hot anymore. So those are all the evolutionary stages of the stars, and their characteristics are based on how big they are, what color they are, and all these other factors we got here. So their surface temperature and color are both given by this bottom axis here, and their luminosity is given by this axis here. Very useful diagram for identifying different types of stars. And as I said before, this clump here, they're going to be the dwarfs, the white dwarfs here, the main sequence here, the giants and the supergiants. And there really aren't many other places that stars can fill. On the right, they're all red. On the blue, on the left, they're all blue. In the middle, they're all yellow. I haven't quite been accurate with my colors. This should be more yellow, and a bigger blue one should be more onto this side. This one should be more blue. That one should be yellow. That lines up a bit better. Okay, hope you learned a lot about stars, the Hertzsprung-Russell diagram, and black body and absorption and emission spectra.